Despite the overwhelming evidence of Venus's present-day hostility, the idea that this planet once had oceans and a temperate climate continues to gain traction. At Infinity Beyond, scientists and enthusiasts alike have become increasingly interested in reconstructing Venus's lost history, not as a science fiction fantasy, but as a data-driven scientific endeavor. With the help of computer simulations and comparative planetology, a growing body of research now paints a compelling picture of ancient Venus as a true water world. One of the most groundbreaking efforts to explore this idea came from a team at NASA's Goddard Institute for Space Studies, GISS. Using Earth-based climate models, modified for Venusian parameters, the team was able to simulate atmospheric behavior on a young Venus, assuming the presence of shallow oceans and an Earth-like atmosphere. The results were stunning, and the model suggested that Venus could have sustained stable surface water for up to 2 billion years. Temperatures would have remained well within the range necessary for liquid water, and perhaps even for life. Days on Venus, lasting over 200 Earth days due to its slow rotation, would have seen long sunrises and sunsets. But with an Earth-like atmosphere, the heat would have been managed through cloud formation and atmospheric circulation. One of the most interesting tweaks the GISS team applied to the model was the proportion of land versus ocean. When they increased the amount of dry land, especially in tropical regions, it dramatically reduced the evaporation rate from the oceans. This helped to prevent a runaway greenhouse effect, suggesting that even with a slow rotation, Venus could have avoided the disaster that eventually unfolded. From the perspective of Infinity Beyond, this is where the science becomes truly awe-inspiring. Imagine a Venus with rivers, lakes, and cloud-covered skies. The highlands we now see through radar, such as Ishtar Terra and Aphrodite Terra, could have been continents rising above shallow seas. The atmosphere would have been breathable, or at least far more benign than the crushing CO2-filled furnace it is today. It's entirely possible that this version of Venus lasted longer than life has existed on Earth. But, like a classical tragedy, Venus's tale turned dark. As the sun continued to brighten with age, a natural process for main sequence stars, Venus's oceans began to evaporate. More water vapor in the atmosphere led to a stronger greenhouse effect, creating a dangerous feedback loop. Eventually, the planet crossed a critical threshold, entering what scientists now call a runaway greenhouse state. Without oceans to trap and cycle carbon dioxide, atmospheric CO2 levels skyrocketed. Surface temperatures rose to extreme levels, and any remaining water was broken apart by solar radiation. Hydrogen escaped into space, while oxygen either bonded with surface minerals or was lost. Venus's skies thickened with clouds of sulfuric acid, and the planet became the hellscape we see today. And yet, the echoes of that lost world remain. Radar data from the Magellan mission in the 1990s helped generate a detailed topographic map of Venus, allowing scientists to reconstruct its ancient terrain. When water is digitally added to the lowest regions of this map, a striking possibility emerges: the outlines of ancient oceans, vast and blue, resting between the highland continents. For researchers at Infinity Beyond, this serves as a haunting reminder. Habitable conditions are not guaranteed to last forever. Planets can change, sometimes slowly, sometimes catastrophically. In Venus, we see not only a twin of Earth, but a shadow of what could have been or might yet be elsewhere in the cosmos. To understand why Venus transformed from a potential paradise to a scorched wasteland, we must look not just at the planet itself, but also at its central star, the Sun. At Infinity Beyond, we often remind our audience that no planet exists in isolation. The fate of a world is intricately tied to the life cycle of its star, and in the case of Venus, the aging Sun played a pivotal role in determining the planet's ultimate downfall. When the solar system was young, the Sun was significantly dimmer than it is today. This faint young Sun phase may seem counterintuitive, but it's a well-understood aspect of stellar evolution. Main sequence stars like our Sun gradually become brighter and hotter as they age. In fact, Astronomers estimate that around 4 billion years ago, the Sun's luminosity was about 30% lower than it is now. This cooler state created ideal conditions for the inner planets, especially Earth and Venus, to host liquid water. On Earth, these conditions allowed early life to emerge in its oceans. On Venus, the same diminished solar output may have sustained shallow seas and a temperate climate. For hundreds of millions, perhaps even billions of years, Venus could have existed in a state not too different from Earth, basking in gentle sunlight with a stable atmosphere and hydrological cycle. But the clock was ticking. As the Sun continued to age, its brightness steadily increased. For Venus, slightly closer to the Sun than Earth, this change had profound consequences. More sunlight meant more energy striking the planet's surface, gradually increasing temperatures. This warming began to evaporate surface water, sending water vapor, an extremely potent greenhouse gas, into the atmosphere. The greenhouse effect is a natural process. It helps maintain habitable temperatures by trapping some of the heat radiated from a planet's surface. On Earth, this process keeps our average temperature at a life-sustaining level. But on Venus, the greenhouse effect spiraled out of control. As more water vapor entered the atmosphere, more heat was trapped, which caused even more water to evaporate, a runaway feedback loop. Eventually, Venus's oceans began to disappear into the sky, not as gentle clouds, but as superheated vapor. Ultraviolet radiation from the Sun broke apart water molecules, releasing hydrogen and oxygen. The light hydrogen atoms escaped into space, while oxygen reacted with surface rocks or was similarly lost. Without water to act as a carbon sink, carbon dioxide accumulated rapidly, amplifying the warming process. The result was a planet-wide transformation. What had once been a blue world turned into a superheated furnace. Surface temperatures soared past 460 degrees, and the atmosphere thickened into a blanket of carbon dioxide nearly 100 times denser than Earth's. Any remaining traces of life, if they had ever existed, would have been obliterated in this slow-motion planetary disaster. For researchers and storytellers at Infinity Beyond, Venus is not just a scientific curiosity, it is a profound warning. The runaway greenhouse effect that consumed Venus is a real physical process, one that can occur on any world under the right conditions. The frightening part is how subtle the tipping point may be. A planet may be perfectly habitable for billions of years, only to cross a threshold that sets it on an irreversible course toward destruction. That's why scientists study Venus so intensely, not only to understand its past, but to better protect our own planet's future. In many ways, Venus shows us the fragility of planetary habitability. The Goldilocks zone isn't simply about distance from a star, it's also about the balance between atmosphere, radiation, and chemistry. And as Venus teaches us, even a planet that starts in the right place can be lost if that balance is broken. The story of Venus serves not only as a record of planetary evolution, but also as a powerful allegory for what can happen when delicate atmospheric balances are lost. At Infinity Beyond, we view the case of Venus as one of the most striking natural experiments in the solar system, a sobering reflection of what awaits a planet when the greenhouse effect spirals unchecked. To fully appreciate the transformation of Venus, we must delve deeper into the physics behind the greenhouse effect. It begins with sunlight, primarily in the visible spectrum, penetrating a planet's atmosphere and reaching the surface. This solar energy heats the surface, which then re-radiates the energy as infrared radiation, essentially thermal energy. Here's the key. While the atmosphere is relatively transparent to visible light, it is far more opaque to infrared. Gases such as carbon dioxide, methane, and water vapor absorb this outgoing radiation, trapping heat and warming the planet. On Earth, this greenhouse effect is what keeps our average surface temperature around 15 degrees, and 59 degrees if I said it, rather than the frigid 18 degrees it would be without it. But the same physical process that protects life can also destroy it. Venus is the perfect example of this extreme. Once Venus began to lose its surface water and increase its atmospheric water vapor content, the greenhouse effect amplified drastically as temperatures soared, all remaining liquid water vaporized. With no oceans left to act as a carbon sink, an essential regulator on Earth, the CO2 levels in the atmosphere ballooned. Eventually, carbon trapped in rocks was also released, further exacerbating the warming. The atmosphere thickened and grew increasingly opaque to infrared radiation, turning Venus into a heat trap from which there was no escape.